Alright guys, so hybridization. um, Here we have, I think I spelled it right, caffeine. If not, sorry. So the question for this is determine the hybridization of all atoms. And I'll do that in purple. We'll do it in this color. And for the second part, determine the bond angles and molecular geometry of oxygen 1 and 2, as well as all the nitrogens, so 1, 2, 3, and 4. So let's jump right into it. So, hybridization of all atoms. First thing I'm going to want to do is to add in the lone pairs. So to do this, I want to check and see if the octets are okay on everything. And so nitrogen 2, 4, 6. No, it's missing a lone pair. Carbon. Each one of these, the CH3, it looks like this. Bop, bop, bop. And then it has its bond to nitrogen, right? You got your H's. So that's perfectly good as far as the what did I do? As far as the octet goes. So, what the fuck? Oh, that's because I'm not trying. So then looking over at this oxygen, 1, 2, so four electrons, or so yeah, 4 electrons. So we need 4 more, right? 2, 4, 6, 8. Beautiful. Now remember what she has said, and myself as well, where the lines come together, that counts as a carbon. So to make this easier to see, I will draw the carbon in right here. This is a carbon right there. There's a carbon right there. There's a carbon right there. Carbon right there. Carbon right there. Okay. So back to where we were. This carbon's good, nitrogen's good, oxygen's good, carbon 2, 4, 6, 8, good. Carbon 2, 4, 6, 8, great. Nitrogen 2, 4, 6. Nope, we're missing a lone pair. I'll draw right here. This carbon right here, 2, 4, 6. No, we're missing something. So instead of drawing a lone pair, in this case, it's going to be a hydrogen. Whenever there's a terminal, like hydrogen set on something, it'll be shown, but where the lines come together, it's just assumed. Yeah, so there's a hydrogen right there. Nitrogen 2, 4, 6, lone pair 8. Carbon 2, 4, 6, 8. Beautiful. Nitrogen 2, 4, 6. Nope. Lone pair. Carbon, remember 2, 4, 6, right? Like I drew in the corner up there before I erased it. And this would be 8, so perfect. And carbon here, 2, 4, 6, 8. Oxygen, 2, 4, 6, 8. Beautiful. All right, so now we have filled octets. Let's go with the hybridization. Now, when determining your hybridization, you want to check your electron groups. So, this carbon right here. Let's look at this. So we have C, H, 3, and then the nitrogen. That's just the snippet of this part right here. Right? And then you bow, and it keeps going. So starting with the hydrogens, theirs is pretty much always going to be just S. So you really don't worry about hybridization because it doesn't happen with them. So with carbon, all you do is count your electron groups. And so if you have 1 electron group, your hybridization is S, hence why hydrogen is always S. If you have 2, Yours is sp3, sp2, 4, sp3, 5, sp3d, and then it keeps going from there. sp3d2 for 6, sp3d3 for 7, so on and so forth. So, looking at this, 1, 2, 3, 4 electron groups. So the hybridization on this carbon right here is going to be sp3. On nitrogen, 1, 2, 3, 4, sp3. Carbon, 1, 2, 3. So it's going to be this one's sp2, I believe. And then oxygen, sp2. This carbon right here, same thing, 3 groups, 1, 2, 3, sp2. Nitrogen, 1, 2, 3, 4 groups, sp2. This carbon is the same as this one, it's going to be sp3, right, because 1 for each of the hydrogens. So 1 sp, p2, sp3. So sp3 for that. This carbon, 1, 2, 3 groups, so it's going to be sp2. This nitrogen, 1, 2, 3 groups, that's going to be sp2. Same thing here, sp2 is 1, 2, 3 groups, sp2. Nitrogen right here, 1, 2, 3, 4, so sp3. Carbon, same thing as this carbon, sp3. Oxygen, 1 group, 2 group, 3 group, so sp2. 1, 2, 3 for this carbon, sp2. And that's all of them. So we've done this part now. Alright, so let's change colors here. Something that's relatively visible. Okay. Bond angles and molecular geometry of oxygen 1 and 2. We'll start there. So oxygen 1, we know it's sp2. It looks like this. And then it continues on from there. So bond angles and molecular geometry. So it's one atom surrounded by 3 groups and only surrounded by 1 atom. So 1 atom surrounded by 3 groups. The electron geometry of that is going to be trigonal planar. If we're looking at the molecular geometry, it's linear, right? Because it's one thing straight, right? So molecular geometry equals linear. Now, if we're looking at the bond angles here, we need to pay attention to the electron geometry. So if we look at trigonal planar, what's the angles on trigonal planar? They're 120, right? Looks like this. Bow, bow, bow. I put a carbon, but okay, we'll do oxygen. And let's say we had carbon, hydrogen, hydrogen. I'm just making something up. The angle's right here, 120 degrees, right? Well, all that's happened is we've gotten rid of these hydrogens and replaced them with lone pair. Right, so let's get rid of that. So it's still 120 degrees. So 120 degrees, but it's also linear when you're talking about molecular geometry. Okay, oxygen 2 just so happens to be the same thing. So 120 degrees, linear. All right, nitrogens. And it looks like 3 of them are going to be the same. So I'm just going to write those real quick. Nitrogen 1, 2, and 3 look like this. We have a nitrogen with CH3, 2 bonds, and a lone pair. So, single atom surrounded by four electron groups, 1, 2, 3, 4. We know that it's going to be sp3, right? And we know, since we're talking about the electron geometry, it's going to be tetrahedral. And the angles on tetrahedral are 109.5, right? And then so if we're talking about molecular geometry, we've lost one atom, which takes us down to trig pyramidal, right? And since we lost that, this is going to repel the other ones. So the true angle is going to be less than 109.5 degrees. All right. So that actually is going to be the same thing for nitrogen 1, 2, and 3. Nitrogen 4, however, is a little different. It has double bond, nitrogen, single bond, and electron group. We know that that's sp2. And we know the electron geometry on that. Since it's a single atom with 1, 2, 3 groups, that's going to be trigonal planar, and the molecular geometry is actually going to be bent, right? Because we've taken away one of the atoms and replaced it with a lone pair. So with trigonal planar, we know it's 120 degrees, but since we have this extra group right here, or the electron group, it's going to repel it. So the actual angle is going to be less than 120 degrees. So this guy right here, angles are less than 120 degrees. Molecular is bent. E, and D. Sorry, that was horrible. And that makes up that part. Let's go to the next one. I have another example. La la la. Come on. Come on, music. Okay. Determine the hybridization, molecular geometry, and bond angles of every atom in Indigo. So I've already started off by figuring out the number of electrons, which is 16, right? We have 2 nitrogens, totaling 10, 1 oxygen, totaling 6, 16. So there's only really 2 ways you could write this. I mean, if you put the O over here, it's the same thing. It's just mirrored. This one has the O in the middle. So let's start with this one. One line that takes care of, so we have 16 minus 4, that's 12. So let's see if we can make the terminals happy. 1, 2, 3, 4, 5, 6. So minus 12, that gives us 0, and oxygen is not happy. So that's not going to work. So then if I go take that away, get rid of it, and let's try a double bond somewhere. So we have, let's try 2 double bonds. So 2, 4, 6, 8, 16, 8. So 2, 4, 6, 8, that takes away 4, that takes away 4, that leaves us with 0, not 8, 0. So let's check formal charge. 6 minus 4 minus 0 equals -2. Now nitrogen, we have 5 minus 2 lines minus 4 dots equals, what's that, -1, right? Yes. And then it'll be the same on this side. So we have negative, and then we have 2 negatives and a negative. So it looks like no matter which way we do this, it's just not going to work. Like, that is way too high of a charge, and if you can tell, this isn't charged. So let's try the other structure. Nitrogen, so 16 minus 4 is 12. Let's try this. And let's just throw a double bond here. So we used 1, 2, 3, 4, 5, 6, 7, 8. So it's 4. So we can put 4 and make this guy happy, but it won't make this guy happy. So let's just do that. Let's see how that works. So that gets rid of 2. Leaves us with 2. And let's see how that works. And not happy, happy, happy. So 1, 2, 0. Let's check our formal charges. 5 minus 3 minus 2 equals 0. 5 minus 4 minus 0 equals positive 1. And then 6 minus 1 minus 6 equals negative 1. So we'll have a, sorry, I'm going to do a different color. We'll have a negative charge here and a positive charge here. And it works out to neutral, right? So that's our structure. So in triple bond, in single bond O, 1, 2, 3, 4, 5, 6. 1, 2. And we do a positive and negative. Okay. So now we want to determine the hybridization. So if we have a triple bond, we have one, let's start here. Lone pair in triple bond. And so we have our atom surrounded by 2 electron groups, surrounded by one molecule. So that's actually going to be linear, and the angle, of course, 180 degrees. Now it's surrounded by 2 electron groups, so this is sp, right? Now if we go to, let me double check myself real quick. Yeah, okay. So 2 electron groups, so the hybridization is just going to be sp. We have the same thing with this. We have 2 electron groups, so it's sp, and they're both going to be 180, right? 180 here, 180 here, 180 here, 180 here. Now with oxygen, you have N-O with 3 electron groups. So the electron geometry is going to be tetrahedral, right? You have 4 groups. But if you're looking at the molecular geometry, it's also going to be linear because you've taken away 3 of those groups. But where it differs is going to be the bond angles. What's the bond angle of tetrahedral? It's 109, right? 109.5 degrees. So the angle between here and here can't be 180. It's actually only going to be 109.5. It's going to be less than 109.5. Or actually, it's going to be, yeah, less than 109.5. No, it'll be equal to, but anyways, 109.5. For the hybridization, so we have 4 electron groups, right? 1, 2, 3, 4. So it's actually going to be sp sp12. Is that sp2? sp3, sorry, sp3. So for oxygen, so for nitrogen fluid, it equals 180 degrees, linear sp, which equals nitrogen 2 as well. And then for oxygen, it's going to be sp3. It's still linear for the molecular, and then 109.5 degrees. And that's that.